So, previous lecture we were talking of nuclear size. So, as you all know, we had discussed it that nucleus is of the order of 10 to the power minus 15 femtometers, of that order. But how do we measure this size? So, what I described last time was you can take electrons of high energy, and those electrons can go and hit the sample, the material in which the nuclei are there, of which you need this radius, and then you measure these scattered electrons as a function of scattering angle. So, how many electrons are scattered at this angle theta? So, as a function of theta you measure that, and from there you can derive the radius of the nucleus, or at least estimate of the radius. Not only estimate of the radius, you can also derive the charge distribution inside this nucleus. In this nucleus, how the charge varies as a function of distance from the center, let us say. So, that also can be done, and what we had seen, the results of these experiments is that if you plot this density, charge density as a function of r, then you find that it is something like some constant value, almost constant value, and then it tapers off. And for different nuclei you have different slightly different values of this, but then the nature is almost the same. Once you convert this charge to mass, right, because the electrons are only looking at the protons, they do not interact with neutrons. So, the results are in terms of the charge density, proton distribution, but then you also have neutrons in the nucleus. So, you scale it up so that protons and neutrons both together, total mass distribution, then all these things coincide and you have almost this type of distribution for. So, this becomes almost same. So, different nuclei will have different extents, but this row here, this row, this is now the number density, how many nucleons per unit volume is there, and this can be written as, so this point is something like say 0.17 or so per femtometer cube, this point, and then this whole structure can be mathematically written as rho equals rho naught 1 plus e power r minus capital R over A. So, this is the kind of distribution. Now, this function, are you familiar with this function? This function is just a mathematical function. If something is nearly constant up to some distance, say x, and then it falls, gradually it falls. So, this kind of data can be fitted with this function. There is nothing fundamental about this. It is not coming from nuclear interactions and nuclear forces or things like that. It is coming, we just see the data, and then we find that okay, this function can be used to explain that data, to understand that data, or to fit that data essentially. Now, this particular function, if you look at it more closely, this rho naught is almost this value. This rho naught here is almost this value, and then there are two more parameters, this capital R and this small a. Now, this capital R, if I just take one of them to understand the function better, take one curve, then what you see is it is constant up to certain r, almost constant up to certain r, and then gradually decreases. So, you can take the point where the density, this number density decreases to half this central value. So, that is this So, that is capital R. This value is capital R. Okay. In this function, this capital R is the value of small r, or the distance from the center where the density means number of nucleons per unit volume, that decreases to half its value. So, that is this capital R. And then this small a, what is this small a? Small a is how fast it decreases from this highest value to almost negligible values. So, that how steeply it falls. If it is just straight away it goes to 0, then this a will be 0, right, but that is not the case. So, there is, so a is something like how gradually or how steeply this density decreases as a function of r. So, if you take 2 points, one point here where the density has become about say 0.9 of rho naught. So, 10% decrease, that is one point. This is also not exactly constant, some slight variation is there. In fact, experimentally if you take the data, then there are more variations, because nucleus is not very smooth inside, there are many zigzags, but roughly. And so, here the density has decreased to 90% of its central value, and similarly you take this point where it decreases to 0.1. Okay. So, this is a measure of how steeply the density is going down from 90% of rho naught to 10% of rho naught, how much distance it takes. So, this can be related to this a, we will make this calculation. So, what is the picture? What is the geometrical picture that coming to mind? Geometrical picture that coming to mind is that nucleus, suppose this is the center. So, you have protons and neutrons here, protons and neutrons, and equal density distribution with equal density, almost equal density. So, whatever is here, number of nucleons per unit volume, same is the number of nucleon here, same is the number of nucleon here. So, it is almost equally dense up to certain distance, and after that the density starts decreasing. After that the density starts decreasing, and then it goes to almost 0. So, this is the kind of nucleus. So, the central core, say this from here to here, the central core has same amount of same number of nucleons. Nucleon, you understand? Nucleon, proton or neutron, collectively they are called nucleons. So, number of nucleons are per unit volume is almost same up to some distance, that is this, and then after that this number of nucleons will gradually decrease per unit volume, gradually decrease, and then finally all the nucleons will be confined to some volume. But then there is no sharp boundary. You cannot draw a line, a circle, a spherical surface that all the nuclei are inside this. This is, it does not fall to 0 sharply. It will become very small, but then 0 it will only be when your small r is infinity. So, nucleus does not have a sharp boundary, right. Nucleus does not have a sharp boundary, the boundary is diffused, the density gradually decreases and becomes negligible. Now, this let us calculate this value 0.9 of rho naught. So, from the center, at what length, at what distance this density falls to 90% of it. One can make easy calculation, 0.9 rho naught should be equal to rho naught divided by 1 plus E r minus capital R by A. So, this is 0.9. So, 1 by 0.9 is equal to 1 plus E r minus capital R by A. So, how much is 1 by 0.9? Quick answer. How much is 1 by 1.1, right? Quick answer, 1.1. This is 1.1. 1.1 into 9 is 1.1 into 9 is 9.9. So, 1.1 into 0.9 will be 0.99, very close to 1. So, it is almost this, and this is equal to this thing 1 plus E r minus capital R by A. That means, this is 1 by 10, 0.1 is e to the power r minus capital R by A, and so r minus capital R by A. How much this should be? How much this should be? Log of 1 by 10. And how much is that? Minus 2.3. Remember, the base of this logarithm is not 10, the base is e. So, this is log of 10 on the base e is 2.3, so 1 by 10, so minus this. So, r is equal to how much? Capital R minus 2.3 into A. So, this is capital R, and there is some value of A, 2.3 times A behind. Here the density will drop off to 90%. So, you can get the meaning of A from here. Similarly, where it goes to 0.1. So, now you can do this calculation. At what value of small r this rho becomes 0.1 times rho naught. The distance where this density falls to 10% of this core value. That one can also calculate, put 0.1 here and then do the similar calculation, and you will find that roughly it is capital R plus similar value 2.2 A or so. So, this separation will be almost 4.4 times A, 4.4 times A. Which separation? The distance at which it falls to 90% and the distance where it falls to 10%, 0.1, right. So, that means essentially it is this. So, you can think of this nucleus in two parts. One is a central core, which is almost uniformly populated by neutrons and protons, and on that there is a shell, there is a cap, and that cap, this thickness is that almost 4.4 A. So, from the data what one finds is that for all kinds of nuclei, heavy, light, medium weight, this A turns out to be almost same, 0.5 femtometer for almost entire range. So, you do the experiment with say carbon nuclei, and from there you get some data, and then from that data you find out how much is A, how much is capital R, how much is rho naught. Then you do the experiment with say nickel, middle weight, zinc, nickel. You do experiments with heavy weights like bismuth or mercury or gold. So, in the entire range one can do the experiment and get the values of this A and this rho naught and this capital R, and what you find is A is almost same. So, that skin thickness or that cap thickness or the surface of the nucleus where the density is decreasing, that cap, that shell, that width is almost same for all nuclei. And if it is 0.5 and then 4.4 times A, so something like 2 or 2.5 femtometer, 2 to 2.5 femtometer will be the shell. And capital R, that capital R is not same for all nuclei. small a is same for almost same for all nuclei, but capital R will be different. And those capital R, if you calculate all those this capital R from different kinds of nuclei, you find that this R turns out to be some constant times A 1 by 3, with this R naught almost 1.2 femtometers. So, A is this, R is this, and then rho naught is also almost same 0.17 nucleons per femtometer cube. So, these are the parameters. So, the core, naturally if you are working with heavier nuclei, then the core will be larger. If you are working with lighter nuclei, the core will be smaller, but the surface is still around 2 femtometer for almost all of them, right. And the density of nucleons in the core, that is also almost same whether you are talking of light nuclei or middle weight nuclei or heavy weight nuclei. So, there.
So, what is A here, capital A?
Oh, okay. Capital A, this capital A is mass number Z plus N, number of protons and plus number of neutrons, that is capital A. So, if you are working, let us say with a carbon 12 nuclei, you have a carbon sample, you have a carbon film, and on the carbon film you are bombarding those electrons and then measuring those number of electrons scattered in different directions, and from there you are deducing what is this capital R. You still get this type of distribution of charge inside, or when you scale up distribution of nucleon numbers, and then you can get that R. That R will be this 1.2 femtometer times 12 to the power 1 by 3. And if you repeat the same experiment with say iron 56, you have an iron foil. In iron foil, most of the nuclei are iron 56, that means 26 protons and 30 neutrons, total 56. So, this capital A is 56. So, this capital R will be 1.2 femtometer times 56 to the power 1 by 3. So, this is capital A is your mass number, depends which nuclei you are measuring at. Okay. So, this R, that mean radius, you can call it mean radius, right, from the center up to the point where the density is decreasing in the skin, the density is decreasing to 50%. So, middle of the skin. So, this is the average or radius, mean radius. So, that mean radius will depend on how heavy is the nucleus, how many total nucleons are there. If you have larger number of total nucleons, then this R will be large, but this A and this A and rho naught, they are almost same for all varieties of nuclei. Okay. Now, you have all the relations. Now, answer roughly what is the radius of a lightweight nucleus, which lightweight nucleus you would like to use. I am looking for this capital R, and I am given you choice. You can choose whatever A you want, but in the light nuclei. So, what value of A you will take, so that calculations is easy. A equal to, let us do it on Excel, right. Let us have some idea which nucleus has what mean radius, and let us use Excel, so that taking cube roots etc. will be simple. Okay. So, I am going to computer, and I will you know all Excel, it is a calculation sheet. You will have some sheet where you will put numbers and formulae, and quickly you will get all those calculations. Okay. So, let me do that. So, you can see that Excel sheet, there is a value 27 there in below that capital A, and then below that capital R is 3.6. So, I have already put a formula there, and what is it is doing, whatever is the value in that cell below capital L, it is taking that as the mass number and calculating 1.2 into that mass number to the power 1 by 3. So, for example, suppose I put 1 here. So, what happens? It should be 1.2. You can see it is 1.2. So, 1.2 into 1 to the power 1 by 3. So, that is here. So, if I use this formula for getting radius of the proton, that will be 1.2 femtometers, right, but that is not good, because all this electron scattering and this that from a nucleus is not for just one proton. I will talk about how much is the proton radius, the charge radius inside the proton. I will talk it later, but this is just for checking that this formula is working well. So, at capital A equal to 1, the value is 1.2, but now let us go somewhere else. So, let us put say 12. So, A equal to 12, what nucleus is this? Carbon. And how much is the mean radius? 2.7 femtometers. Do not go on 2.74731, this is just calculations. When you take cube root, it is an unending series. So, it will cut wherever is the limit of this calculator. Okay. So, it is say 2.7 femtometers. Then let us see 60, somewhere around nickel, 4.7 femtometers is the mean radius. Then go somewhere, let us say 100, 5.5 femtometers. Now, tell me a heavy nucleus that you know, name of a heavy nucleus that you know, very heavy, uranium, 235, correct, capital A is 235. So, let us go for that, 235, 7.4 femtometers. So, starting from say nearly 2 femtometers for light nuclei, even for the very heavy nuclei it is 7.4 femtometers. If you go for more exotic things, say 280 or so, 7.8 femtometers. So, now you have some idea of how big is the nucleus, right. Okay, so, I am coming to the board once again. So, that means all these nuclei starting from very light nuclei to very heavy nuclei, the nuclear size is does not vary much. The nuclear size is from say 2 femtometers to 8 femtometers, 7.5 femtometers. In this, the entire thing, the whole range of nuclei that is available has this kind of radius. Now, what I would expect, I will ask, let me ask a question. The nucleus is there because of nuclear attractive forces, because inside the nucleus you have protons and protons repel each other, and therefore, the nucleus should just fly apart, Coulomb repulsion. But if the nucleus is there intact, it is because of the nuclear forces which are attractive in this separation range and which are much more dominant than Coulomb repulsion. So, if it is there because of this attractive force, why it is not that at the center things are more crowded, because the attraction will be towards the center, right. Just like say Earth's core, Earth is there because of that gravitational attraction. So, the density at the core is much higher, and as you come towards the surface, the density starts decreasing there itself. Okay. You come 500 kilometers from the center and you say that the density is significantly dropped, then 1000 kilometer and 2000 kilometer and so on. Sun's core, once again the density in the core is very high, and as you come out the density is gradually decreases, but here the density remains same up to the last 2 femtometers, that last shell. So, can you see some, can you draw some conclusion from here? why it is not crowded at the center if it is because of the attraction. Atmosphere, look at the atmosphere, the density here at the surface of the earth is larger, and as you go up the density gradually decreases. So, if there is an attractive force which is pulling it down, the density is likely to be more as you go towards that attraction center, but here it is not. This has a very important physics behind, and that physics is that nuclear forces are short ranged, this part here does not have much influence on this part here. So, it is not that the entire thing is getting attracted towards the center, this is being attracted by only these nucleons, it is short range. So, because of that short range, whether it is here or here or here or here or here, you do not have too much of crowding at the center, right. Okay. Now, let me give one more process by which people measure this radius of nucleus. So, this is one experimental process that I described last lecture, and one more process I would like to give. And that has to do something with the atoms and the atomic energies. So, we are talking of nucleus, but then this method that I am going to describe to measure the radius of a nucleus depends on the electrons of the atom in which this nucleus is at the center. So, if you look at the atomic structure, you have a nucleus here and then you have electrons around. I will not draw those circles which are there in elementary textbooks, Bohr's circular orbit, right. Bohr's circular orbit is something which gave very good explanation or understanding of those hydrogen spectral lines, but once the sensitivity of apparatus increased, find the structure of hydrogen, all those things came in, then one had to do a better modeling in terms of quantum mechanics. So, how do you get the energy of this atom? Let us say for hydrogen atom. Remember your classes, quantum mechanics classes of hydrogen atom or hydrogen like atom, ions, just one electron, ions with one electron left. So, then your potential energy term would be minus ZE square over 4 pi epsilon naught r. ZE is the nuclear charge, positive nuclear charge, minus E is the electronic charge. So, the energy of electron we are looking for. So, potential energy will be this. With this potential energy, you will write this time independent Schrodinger equation H psi equal to E psi, right. This E will have a kinetic energy part, no H, this H will have a kinetic energy part, this is Hamiltonian, which will be minus H cross square by 2m, and then the potential energy part. So, with this Hamiltonian, you will solve this equation to get the energies, and then you find that there are too many levels, n equal to 1, n equal to 2, n equal to 3 and so on, right, that way. Now, if you when you solve this and the lowest energy, look at the lowest energy. How much is this? Remember, for hydrogen almost minus 13.6 eV. I can write in terms of fundamental constants H cross and mass of electron and this and that. So some energy is obtained. Okay. And what is the wave function corresponding to the hydrogen like atom, you generally write it 0 0 0 or 1 0 0, n equal to 1 1 0 0. This will be pi a naught cube here and z here cube, z cube here, square root of this, e to the power minus z r. What is z? Number of protons in the nucleus. And what is this a naught? Bohr radius, right, Bohr radius. So, this is the wave function for the first lowest energy. Now, this wave function is not 0 at r equal to 0, right. If you put r equal to 0 here, this will be e to the power minus z minus 0, r is 0, which will be 1. So, it is not 0. So, this is not 0 at r equal to 0. So, that means it is going through that nucleus. The nucleus is at r equal to 0 and this wave function is not 0 there. So, that means there is a probability of finding the electron right at the site of the nucleus. So, if the nucleus is penetrating this electron is penetrating the nucleus, then any structure in the nucleus will affect it. Now, this Coulomb potential that you have written, Coulomb potential energy that you have written assumes that nucleus is just a single mathematical point at the center, at the origin. That is why I have written it like this. But if the nucleus has a radius, if the nucleus is like a sphere, not like a point, and this electron is penetrating in there, this electron is going close to r equal to 0 and it is going to r equal to 0, then whether it is a point, whether it is a sphere, whether it is a small sphere, whether it is a big sphere, is going to affect the energy. And how much is this changed? That is related to how big is the nucleus. If the nucleus is really like a point charge, then this relation will be okay. But if the nucleus is not like that and it is an extended sphere, then the energy will be different, and if this difference in energy can be measured, then from there we will be able to know how much is the radius of this nucleus, right. So, let us give it a try, right. I will make so many assumptions, but still let us make it an attempt. So, what I will do, what is the change? Change is in potential energy. Look at the Hamiltonian, the kinetic energy will remain the same, that term minus h cross square by 2m del square, that will remain the same. It is only the potential energy which is getting changed. So, this potential energy is minus ZE square over 4 pi epsilon naught r for point nucleus. If I assume that the nucleus is a point, then this is it. Now, assume that it is a spherical nucleus. Suppose it is a spherical nucleus of radius r, and also charge is uniformly distributed. Let us make all these assumptions to get an estimate. Charge is uniformly distributed. Which charge? Which charge is this I am talking? Which charge I am talking? Nuclear charge. Nucleus is a sphere and all those ZE charge is uniformly distributed. Then how do I get the potential energy? So, now I have a sphere of radius r and then the charge is uniformly distributed here. Nuclear charge, positive charge is distributed here. Total charge is ZE. Total charge is ZE. First, let us write potential. Now, remember your electrostatic lessons. If you have a uniformly distributed spherical charge distribution and total charge is given and the radius is given, you can write potentials, electric potential. Outside this sphere, it is all the same whether this is extended or it is a point charge. Remember that? Outside this sphere, the electric field potential is same as if this whole thing is concentrated at its center. So, for outside, for r greater than capital R, V I am now writing for potential, not for energy. Okay, this is energy. So, let me give some other name. Let me call it U, potential energy. Here I am only writing potential. V at R will be Z E over 4 pi epsilon naught R. Right? This is because for an outside point, the spherical distribution, spherical charge distribution can be considered to be a point, everything concentrated at its center, point charge. So, it is this, but inside the story is different. So, up to here the potential I know, all outside point up to here the potential I know, V at capital R I know, V at capital R will be Z E by 4 pi epsilon naught capital R. Now, I am getting into the sphere. So, how do I calculate potential? Get electric field, get electric field inside first and then integrate electric field to get the potential difference and add to this potential. So, what is the electric field? Z E total charge 4 pi epsilon naught and then R here and capital R square here and R cap here. So, the potential here at some point R, V at small r and minus V at capital R. So, I am taking potential difference between some point inside and the surface, right, V r minus V capital R. This is by definition minus integration from capital R to small r E dot dr. That is how you define potential difference, V r minus V r. So, you have this is equal to V small r minus V capital R is equal to minus integration from capital R to small r E dot dr. Here is electric field. Now, I am talking of inside. So, here is the electric field. It is Z E r divided by 4 pi epsilon naught capital R square R unit vector and dot that dr. So, it is just dr, right. This dr also has unit vector r cap. So, dot product of this r cap with that r cap will be 1 and it is this dr. So, integrate. This is equal to minus Z E over 4 pi epsilon naught r square. So, minus Z E 4 pi epsilon naught r square r dr, which is r square by 2 and then put the limits. So, it is r square minus capital R square by 2 and hence this V at R is equal to V at capital R plus this, right, and V at capital R I can write from here, V at capital R I can write from here, that will be Z E over 4 pi epsilon naught capital R and then minus Z E over 4 pi epsilon naught R square and R square minus R square by 2. I have gotten the potential at that distance r. Can make some simplifications. I can take something common, Z E by 4 pi epsilon naught r common. So, it is 1 here and then it is minus r square by 2, this r square is there, right. What is this? Let me. So, this I have taken common. So, 1 will be there minus and then Z E I have taken, 4 pi epsilon naught I have taken, R I have taken. So, one R will be there. Okay. Let me take this bracket. So, that this minus is outside and then this bracket. So, 4 R square, small r square by 2 capital R minus 1 by no right, check, correct. Okay, good. So, make it better looking, but this is wrong, this cannot be correct, this expression cannot be correct. This has to be wrong, because the thing that you have told here has a dimension of length, it is r square divided by r, and this is dimensionless. You cannot add dimensionless quantity to a quantity with dimensions. Can you do that? And that is because this expression itself is wrong. Here this is dimension, this r square by r square, correct, and whereas here it is 1 by r. So, take from here V at r, let us check everything. Is this electric field? No, it is not electric field. It is not electric field. This is electric field. The electric field should be q by r square, q by 4 pi epsilon naught r square. So, here is q, and then 4 pi epsilon, it should be 1 by r square. It should have a dimension of 1 by r square. So, if it is small r here, it has to be capital R cube here. So, that error is coming from there. So, make correction in the previous thing also. So, you have this r cube here, and therefore, you have this r cube here, and therefore, what happens now? Now, what happens? 1 by r, and this is 1 by 2. Okay? Now, it looks fine. This is dimensionless, r square by r square. This is dimensionless, 1 by 2. This is dimensionless, 1. So, everything is consistent. So, make this a practice. Whenever you do algebra and you get expressions, periodically you see whether all terms have same dimensions or not. If they are not, trace the error, somewhere error has been made. All right. So, this is equal to Z E by 4 pi epsilon naught r, capital R, and then 3 by 2 minus r square by 2 r square. So, you can write this as Z E over 8 pi epsilon naught capital R and 3 minus r square by capital R square. What is this quantity we have gotten? This is potential at a distance small r from the nucleus inside that nucleus, that is this. So, point nucleus you remember, you know, and this spherical nucleus now you know. So, how much is the change? This will be and minus Z E by 4 pi epsilon naught r. This is the potential assuming nucleus to be a point charge, and this is the potential assuming nucleus to be a uniform sphere. So, that is the difference in potential, and therefore, the difference in potential energy multiplied by minus E, multiplied by minus E. So, this will be minus Z E square by 8 pi epsilon naught r 3 minus r square by capital R square, and then minus z e square over 4 pi epsilon naught r. Okay. Now, little bit on quantum mechanics. What I have obtained is the change that you have to bring in if you want to write the spherical nucleus potential. Right. Now, look at the Hamiltonian. The Hamiltonian is also changed by this amount. It was minus h cross by square by 2 m del square plus potential energy. Potential energy is changed by this amount. So, Hamiltonian is also changed by this amount. So, original Hamiltonian, I can now erase all this. The original Hamiltonian, original means with point nucleus, H with point nucleus, assuming that the nucleus is just a point, call it H naught, and then the Hamiltonian with extended nucleus is H naught plus H 1, and this H 1 is given by this expression that is there. Is this fine? Right. This is the change in that potential energy term, kinetic energy term remains the same. So, change in Hamiltonian that I have to bring in, this extra term that I have to bring in is just this. Now, how it affects the energy? Remember, energy we have gotten from solving the Schrodinger equation H psi equal to E psi. Now, H has become H naught plus H 1, previously it was H naught, and now it has become H naught plus H 1. So, now we have to again solve this H naught plus H 1. With this I have to solve this. This is the new energy. Okay, this is the new energy. So, I should use this Hamiltonian and get the energy, and for that the quantum mechanics rules are, or the procedure is quite simple. First order correction, okay, the first order correction is done by what you called first order perturbation theory, and that is that from this H naught, first you get this wave function from, call it, you can call it H psi naught or psi point or whatever, from H naught, get this wave function from H naught, and if H 1 is a small correction in H naught, this procedure works, that get your wave function from H naught and use that wave function to calculate delta E, which is that psi naught here and this H 1 here and psi naught here. Remember that?
Okay.
And what does this mean? Let me erase this also. What does this mean? This is integration psi star and then this H 1, that operator H 1, here this will be just delta U that I have calculated, and psi naught r and then d tau. And since that the kinetic energy term is not there, a del square term is not there, it is just multiplication, right. That kinetic energy term differentiates, whereas this potential energy term just multiplies. So, it will be, so multiply this and this, mod psi naught r square into this delta U that you have calculated times d tau. So, we will stop here, and next class we will start from here, we will do some integrations and we will calculate the change in the energy, and from there how do I get the radius of the nucleus, that will be our next lecture's topic.